All right, late night AP Physics C derivations of inertia. So here we go. We have these three masses. They're rotated about this axis. And as they rotate, they're going to resist the motion. Inertia is the resistance to change. The more mass you have, the more resistant you are to change. F equals ma. It's also in the rotational realm as well. The more mass you have, the more resistant you are to change, and where that mass is placed determines the resistance as well. So here's what we're looking at. Inertia, in the rotational sense, is equal to the mass times its distance away from an axis of rotation squared. What we see there is that the distance is way more important than the mass because of that square. Now, if we have a system of masses, we can take each individual mass and add their inertias together to get the inertia of the system. We can't just say the mass plus mass plus the mass times some average number is going to be the inertia of the system. So here we are. The sum of the inertia here is equal to this one plus this one plus this one. Let's start with this one. M R squared. Simple as that. Next one. Choose this guy over there. M R is actually 2R squared. Third one, M again, 3R squared. Alright, now the square thing kind of tells us that this will become a 4mr squared, and this one will become a 9mr squared. And this is a mr squared. So we have 1mr squared plus 4mr squared plus 9mr squared, so that's going to be 14mr squared. So 14mr squared is the inertia of this system, and that's the simple, I'm going to add up all these point masses way. Now, as we get to objects, we need to figure out the inertia of objects that are not just point masses. But we treat it kind of the same way in a calculus sense. So here's a rod. It's of mass m, and it's of length L. Or we can even say capital L if you want. So what we have here is the inertia of this rod with mass m, length L, and you might say, oh, well, the center of mass is at the center, and so the inertia of it is 0 because r is 0, and that's totally wrong. So don't do that. What we need to do is we need to look at the inertia equation, and we need to consider that here we have a bunch of small masses. And I'm going to cut this thing up into many, many small mass pieces along the x-axis here. And so instead of m, we're going to have something called dm, and that's r squared there. And the reason why I call it dm, calculus thing, is because a small change of something is delta. We'll have a small change of m. If the change is super, super, super small, delta is no longer really appropriate. We're going to change that into a d for a dm, and that's going to be one of these things. All right, just one of them. And keep in mind, there are billions of these. There are so many that you cannot count, but we'll just say there's a billion. We're just going to pick one of them. So that's what dm is. And if we have one of these little masses times its radius away from the center squared, we get a little bit of the inertia. And the idea is we're going to add all those together to get the inertia of this rod. Now I know that the inertia of a rod is 1/12 the mass of the rod times the length of it squared. So I know that. And here we're just going to prove it. So in order to prove it, we need to determine what the mass is of one of those things. So this is where this idea of density comes into play. This mass of the entire thing is spread out over the length of the entire thing. And if we multiply this by some length, then we should get some mass. So imagine if we multiplied this ratio by big L, then we should get m. And you should see that. But if we multiplied it by any other length, we should get any other mass. Now we want this piece right here, so we're going to say that is of length dl. Alright? And so we're going to multiply this mass over length by a dl. And what this should give us is a small mass, which is what's called dm. Alright, so this idea of dl it's one full piece. It's not d times L. It's literally one full thing, and that's going to represent a small, infinitesimally small piece of whatever we're talking about. Same for this one over here, and we're going to plug that in to dm in the equation. So the small inertia here is equivalent to dm, which is going to be m over big L times dl, and this is going to be multiplied by r squared. Well, r squared is more like an L squared here, if you can imagine that. It's this distance away, and I'm still calling big L this whole distance. Little L is going to be some from here to there, or from here to here, or from there to there. It's going to change. Little L is the one that's going to change. DL is not the same. It's just a little chunk of this big L piece, and so we have an equation that defines the inertia of just one of those little boxes. Then the question becomes, well, how much do we want to add up together? And you can add up half of it, this half, you can add up this half, but we're going to add up the whole thing. We want all the inertia. We want from the beginning to the end, from 0 to L. And so let's rearrange this real quick. I can pull out those constants, m over L, and I get the integration of 0 to L, this L squared dl. And using the power rule, the L squared becomes L cubed. And so we have L cubed over 3. And I have a range from 0 to L. But wait a minute. Don't we have... We should be going from here to here. Negative L to L. Or we can just double this. So whichever way you want, I'm just going to go from here to there, and using symmetry, we'll just double it. And then we're going to plug in these boundaries. So the way that you use this thing here is that we're going to plug in the top one in for L, and then we're going to subtract the bottom one plugged in for L. So if we have this equation, I've got 2m over L with big L plugged in, cubed over 3. And if you subtract, we're going to subtract the 0 plugged in. Well, I'm just going to get 0 there. So, looking at this thing, what starts to cancel out? Well, we've got L there. No, oh, she wants to go outside. We've got 2/3 m. Uh-oh, L squared. There's something wrong with this. What is wrong with this? Oh, you know why? It's because it's not L. We're not going from 0 to L. The whole thing is L. We're going from 0 to L over 2. So let's try this again. Sorry for the pause there, but I was just thinking something's wrong. Our integration's not from 0 to L, it's 0 to L over 2. And if you were thinking that a couple minutes ago, thank you. Thanks for screaming out that I was doing it wrong. But we'll plug this in again. So we have 2m over L. I've got L over 2 plugged in, cubed, divided by 3. This is going to be 2m over L. I've got L cubed there. 2 times 2 is 4 times 2 is 8. I've got 8. I've got times 3 right there. Let's see what happens here. 2 and 8, that becomes a fourth. So 1/4 times 1/3, that's going to be 12. L's cancel out. 2 now. And I've got ml squared. Look at that. Okay, that was a little screw up there. Sorry about that. But we did get 1/12 ml squared. We'll do it again. I've got this little thing down here. Talk about this. We've got some mass of a disk spread out. This radius is r, big R. And so we're going to use the exact same idea, that a small piece of the inertia should be equal to a small piece of the mass times its distance away from a center of rotation. So our job here is to figure out what the heck is dm. And one way to do it would be to look at this thing radially. And so we're going to look at this, and we're going to cut it up into pieces that look like this. Alright, so we're going to take one of these. One of those is going to be a dm. And if we take one of those as a dm and we have this ring, imagine you have an onion ring, and you snip it and you roll it out, then what you get is this rectangle. And that rectangle has a length of 2 pi r. I'm not going to say big R, I'm going to say little r. And it's got a thickness that is going to be dr. Alright, it's going to be a thickness of dr. Can you see why? A little thickness. And dr is going to go from 0 all the way to r. We're going to add up all those drs. Alright, and so what we're going to look at is this dm. dm is going to be this mass spread out over all this area, and this area we're not going to care about the thickness of it really. We're going to care about the pizza pie shape. 2 pi r. Actually, not 2 pi r. Pi r squared. It's getting late. Second time I made the video because I screwed up before. Surprising that I screwed up again. But here, m over pi r squared. So we've got this ratio, this density ratio. This is the area of the circle. If we multiply this by an area, a dA, then we should get a dm. So we look at this. The area of this rectangle is 2 pi r dr. And so here's the mass over the area times 2 pi r, little r, dr. And that's dm. Okay? Clean it up a little bit. Cancels out right there. We've got dm is equal to m over big R squared 2 r dr. Make sure we didn't lose anything. We're going to plug it into our original formula right there, dm r squared. So dm r squared is all of this stuff. dr times r squared, which make this an r cubed. And this is equal to a di. And we want all of it. From 0 to big R, from 0 to I, we want all of it. And so we integrate, and we notice that this is a constant, this is a constant, that's a constant, everything's a constant except for r cubed, and we need the dr in order to integrate. So I'm going to pull the constants out. They aren't changed by your integration. And the r cubed becomes r4 over 4 whenever you integrate. And then my bounds are from 0 to r. And so we plug in. And when you plug in, you get 2 over 4 is 1/2 m r to the 4th over r to the 2nd. This is equal to 1/2 m r squared. And that is exactly what we should expect if we already went through this in class. The inertia of a disk, a solid disk, is 1/2 mr squared. If you wanted to consider a cylinder that's hollow, you wouldn't go from 0 to r, you'd go from like half r to r. So, basic integration with inertia. Very last thing that we're going to do is a little bit of an Easter egg. Because for this year, I'm not sure how long this video is going to be online or how many years of physics are going to look at this video, but there's a test coming up. And I told you that I would put an integration problem on your test. And this is it. So, a little bit of an Easter egg for you there. That this next problem coming up is our Easter egg problem. So here you go. This problem, which will be on your test in at least this format plus a little bit more, but this is your basic integration of it. This is me. What the? Alright. So we're gonna say we have something that looks like this, and it's gonna be like this, and I can't see where my fingers are. Here we are. Alright, we're gonna have this. This is a triangle of mass m, and it's of height L, and it's of length 2L. And you need to find the inertia of this. Now, if you were thinking center of mass, we've already done center of mass in class, hopefully. Center of mass of a triangle is going to be 1/3 the side, so somewhere around here, and 1/3 the side, so somewhere around here it's closer to the fat side. But we're not doing that. We're going to do the inertia of a triangle, like a triangular plate. And that's not something we would have done in class yet. So Easter egg, here you go. I'm expecting you to know the method. I'm expecting you to know the answer. We're going to try to do this without numbers here. We'll see what that gets. I tried it before with numbers and I got all jacked up looking. So let's try this. So the idea, again, is we need to look at a small piece of the inertia, which would be based off a small piece of the mass times its distance from the axis squared. And then we're going to add up all these things. So a good bet would be to say, hey, what's dm? And if I have this shape, I'm going to think that these would be nice to chop this up, and maybe we pick one of these and we'll call that dm. Alright, so one of those is dm. Now, how do you find the mass of one of those? We take this mass and we spread it over the area, and we multiply this ratio, this density ratio, by some small piece of the area, and we should get some small piece of the mass. Alright, so now the question remains, what the heck is the area? Area and d area. Well, d area would be this shape here. Now, this piece is so long compared to how thick it is that this little junk here doesn't matter. I don't care about that. So on the bottom we're going to have a dl here, and with the height of this would be some y value, and y is going to change. Y is going to start off at L and go down to 0. So y would be based upon where you are at the moment along this axis, and let's see, we need to fit it into this, y equals mx plus b. So the plus b is going to be L, because that's where y-intercept is, and the slope here is down L over 2L, so it's 1/2. And we can call this R, I guess. This is like an R right here. 0 to L, 2L would be R, and that's y. So let's see, negative 1/2 R plus L, and let's just make sure this matches up. If R is 0, the height is L. If R is 2L, then we get 0, and that's good. So dA, the area of this thing, is the base of this thing times the height of this thing. Like that. That's dA. That's going to go right there. dm is all this. We might want to find what A is. It's a triangle, so A would be equal to half the base times the height. So that goes away, that goes away. A is equal to L squared. Okay, so dm, let's go all the way down here. dm is equal to m over L squared times dA, which is going to be negative 1/2 R plus L dL. Or dr. We'll use that one, dr. Because R is going to be this thing here. L would be the length, or 2L, or L. So, that's good. Like that. I'm going to put it in right there. So, Adele. All this crap. Half R plus L. My dog wants to go outside. dr. And there's another R here. So we'll put it over here, R squared. Now we're just doing algebra, I think. Well, a little bit of calculus left. Let's see. Let's go ahead and distribute this r squared through. So I've got, we'll do that. M over L squared. I've got negative r cubed divided by 2 plus r squared L dr. And that's di, and we're there. All right. So all this is really mr squared. But m is defined by all this junk here. Okay, so don't lose your mind of where we're at. dm r squared, right there. This is dm, and there's the r squared already distributed through. We need to add up all of it. From 0 to all the inertia. From 0 to 2L. That's what we're adding up. And let's go ahead and pull out some of these constants here. ML squared is a constant, so we can just take that out first. And when we integrate, we're going to integrate r cubed. R cubed is going to become r4 over 4. 4 times 2, though, is 8. Plus L, r squared becomes r cubed over 3. And this goes from 0 to 2L. Okay, oh, sorry, wasn't in the camera. My bad. Just hold it there for a second, let you catch up. This is a video, so you can just pause it. Alright, we're going to plug in the 2L to the top. R is right there. We're going to plug in the 0. Notice if I plug in 0, that becomes 0, that becomes 0. Everything becomes 0. So the inertia that we're looking for is just the 2L plugged in. I got m over L squared negative 2L to the 4th over 8 plus L 2L to the 3rd over 3. Uh-oh. How are we doing this? Does this look nice? It's starting to look not nice. We'll figure it out. I'm going to distribute the L squared through. I'm going to keep the M on the outside. I've got negative 2 becomes... Ooh, crap. It's 2 times 2 times 2 times 2. 2 to the 4. Why am I... No, 16. 16 L4 over 8 L squared. That's going through. Plus 2 times 2 times 2. 8. 8 L to the, to the 4 divided by 3 L. This is working out nicely. Okay, all right. So that goes away with that. That becomes L squared. That goes away. That goes away. That becomes L squared. So that's good. We can pull an L squared out. So that goes away. Okay, and so now we have M L squared. And these fractions in here, I've got negative 16 over 8, that's negative 2, plus 8 over, that's not nice. Alright, so we've got negative 2 plus 8 over 3, common denominator here, 2 over 1 is negative 2 over 3, so negative 6 over 3. Plus 8 over 3. That's good news, because negative 6 plus 8 is still 2/3. Holy crap. So, 2/3 at the end of my page, ML squared is equal to the inertia. Ladies and gentlemen, holy effing mu. 2/3 ML squared from all that. So there is your triangle. And we got an inertia for that triangular shape of 2/3 ML squared. Alright, cool. I'm going to keep it like that. End of video. I'm going to try to make this a good size. Alright, good night.